This topic on path planning and trajectory generation is very much related to the Jacobian matrix topic we learned last time. So you will see the Jacobian matrix popping up in this lecture also, and you will have some more opportunities to practice it. In the past, we have only paid attention to the positions we want the end effector to reach. For example, in the final challenge in Robotics 1, we programmed the robot to move the end effector to a pick location to pick up an object, then to move to a place or drop location to drop the object. We didn't really pay attention to how the end effector moved between these 2 points, or the path that the end effector took. In practice, the path taken by the end effector between 2 points can be immensely important. For example, if the end effector is a cutting tool, a laser for engraving, a drawing utensil, a spray paint can, or something like that, the path of the end effector determines what is cut out, drawn, painted, and so on. The process of controlling the path that the end effector takes between 2 points can be broken down into 2 components: path planning and trajectory generation. Path planning is the step where we figure out where in space we want the end effector to go between 2 points. We call this the path. We might define this path as a bunch of points in the order that we want the end effector to reach them, or more commonly, we might define the path as an equation. Now, when we actually make the end effector follow the path, we also have to define the speed at which the end effector should be moving along the path. This is where the step of trajectory generation comes in. The term trajectory effectively means the same thing as velocity. It includes both the speed that the end effector is moving and the direction that the end effector is moving in. We will get the end effector to follow our path at a specified speed by setting the trajectory or velocity of the end effector. Let me start by giving a simple example. Suppose that we want the end effector to move from point x1, y1 over here to point x2, y2 over here. First, we plan the path. Let's say that we want the path to be a straight line. We want to define this line as an equation. Of course, we all know several different ways to write equations for lines. We could use the point-slope form, or we could use the 2-point form, for example. But when we're doing path planning in robotics, there is a particular kind of path equation that is most useful to us. It's called a parametric equation. A parametric equation defines the points on a path relative to a parameter that varies from one value at one end of the path to another value at the other end of the path. The meaning of the parameter could be a number of different things, but for our uses, we want the parameter to represent time. If we do that, it will make our trajectory generation step easier. So let's write a parametric equation for this line. We will have one equation that says the value of x at any point in time, and one equation that says the value of y at any point in time. The parametric equation of a line looks like this. Here, t is the current time, and v is the velocity of the end effector, the speed at which we want the end effector to be moving through space. We have one equation to find the x position of the end effector at any point in time, and one equation to find the y position of the end effector at any point in time. So now that we have the parametric equation for the path that we want the end effector to follow, it's time to do the trajectory generation step. In order to do that, we're going to take the time derivative of x and y to get x dot and y dot. Now, let's pause for a moment to think through the meaning of these equations. Suppose we want to move the end effector in a straight line in the x direction. In that case, y2 minus y1 would be equal to 0. And this whole equation ends up being just x dot equals v, the velocity of the end effector, which is what we would expect. And y dot would end up just being 0. Similarly, suppose we want to move the end effector in a straight line in the y direction. In that case, x2 minus x1 would be 0. And so the y dot equation simplifies down to just y dot equals v, which is also what we would expect with x dot being equal to 0. But you can use these two equations to get the end effector to travel in any line defined by the 2 points x1, y1 and x2, y2. Okay, now that we have x dot and y dot, can you start to see how this might connect up with what we just learned about the Jacobian matrix? As a reminder, we learned that the Jacobian matrix equation looks like this. Now, suppose that we know what we want x dot and y dot to be, because we just figured it out with our path planning and trajectory generation. Could we use the Jacobian matrix to figure out what the joint velocities should be to get those end effector velocities? We can, but our Jacobian matrix isn't arranged correctly for that right now. This arrangement allows us to calculate the end effector velocities given the joint velocities. But we actually want to do it in reverse. Given the end effector velocities, find the joint velocities. I want to get rid of this Jacobian matrix on the right side of the equation. If this was just a single number rather than a whole matrix, I could get rid of the j by just dividing it out. But it turns out that we can't really do that with matrices. Instead, we have to use something called the matrix inverse. The matrix inverse is signified by putting a -1 as the exponent of the variable. So the inverse of the matrix J is J to the -1 power. Now, if I multiply the right-hand side of this equation by J to the -1 on the left, like this, and I also multiply the left-hand side by J to the -1 on the left, the equation will stay the same. It's just like if I had multiplied both sides by 5 or something like that. The whole equation would still be true. Now, I need you to remember some more things that you probably learned about in linear algebra in the past. A matrix inverse times a matrix is equal to the identity matrix. And the identity matrix is the matrix version of the number 1. So this whole thing here just goes away because it becomes 1. And we have solved this equation for the joint variable velocities. Just like we can find the end effector velocities by multiplying the Jacobian matrix times the joint variable velocities, we can find the joint variable velocities by multiplying the inverse of the Jacobian matrix times the end effector velocities. So we already know how to find a Jacobian matrix. How do we find the inverse of a Jacobian matrix? First, we have to split up our Jacobian matrix. It turns out that we can't control more parts of the velocity than we have joints. So I can only calculate the inverse of the whole Jacobian matrix if we have 6 joints. Then we could control all 6 parts of the velocity together. But let's suppose that you are trying to control the velocities of your Scala manipulator, as we're going to do in this part of the class. For now, we're going to ignore the third joint, the prismatic joint, which is our rack and pinion. In this case, we only have 2 joints, so we can only control 2 of the velocities. That's okay, because in our line example, I really only care about the linear velocity in x and the linear velocity in y. So I'm going to make a simplified version of the Jacobian matrix that only includes these two things. That's necessary because we can only find the inverse of a matrix that is square. So now that we have a 2 by 2 matrix, the matrix inverse is defined like this. Let's do this for our Scala manipulator. First, we have to find the Jacobian matrix for the Scala manipulator. The Scala manipulator has 2 revolute joints, so I'll get the revolute part of the Jacobian table and fill them in like this. First, R00 is super easy because there is never any rotation of a frame relative to itself. So R00 is just the identity matrix. I take the third column and fill it in here. Next, let's do D02. That comes from the matrix H02. It's found in the upper right-hand corner. In the section on Dennevit-Hartenberg, you already found the homogeneous transformation matrix, and you probably found it to be something like this. So we'll pull out D02, and then we'll cross it with 001 and get the following result. Okay, now how do I get D01 and R01? I get those from H01, which we also found in the section on Dennevit-Hartenberg. I found H01 to be this. So I take the third column of the rotation part, which is 001, and then I take D02 and I subtract D01, which is in the upper right-hand corner of H01. I cross them together and I fill it into the Jacobian like this. Now, I really don't want to write out these crazy long expressions anymore, so I'm going to call them J11, J12, J21, and J22 from here on out. In this terminology, the first number refers to the row and the second number to the column. So J12 means the expression that's in row 1, column 2. Now, since I'm only going to control the x and y linear velocities, I'm only going to take the first 2 rows of this matrix, and I'll make a simplified equation that looks like this. Now, I want to solve this equation so that it says theta 1 dot and theta 2 dot is equal to the inverse Jacobian times x dot and y dot. So I have to find the inverse Jacobian. I'll use the definition of the matrix inverse to find the inverse Jacobian like this. This gives us 2 equations. Now we're actually done with all the tasks we need to do, but it's a little hard to see how we're going to use this to actually control the end effector velocity. So let's go write some code to do it. We'll do that in the next video.